Okay, let's go ahead and get this show on the road. Like I said, my name is Darren Jones. I'm a solution architect at Andes. And I'm going to be talking about sort of the promise of RISC-V, which is to customize your instruction set for your workloads, and some challenges there, and hopefully some solutions as well. First, a little bit about Andes. I think most of you guys should know us by now. You've all walked past our booth as you entered the hall. We're a large pure-play CPU IP company based out of Taiwan. We have development offices throughout the world. In addition to Taiwan, there's also 3 different offices here in the US. Very large company, over 500 employees. We have a range of processors in our product line, ranging from small microcontrollers, very small, very efficient, very low power, all the way up to very high performance, out-of-order machines, as well as the sort of what I call the workhorse processors in the middle there, dual issue. We have 32-bit flavors, 64-bit flavors, and you can see on the right side there's even a family of functional safety and processors suitable for automotive. So that's kind of the plug for Andy's products, but what I'm going to talk about is really the promise of RISC-V and how do we add instructions. And for Andy's processors, you can do that throughout the product line, both low-end and high-end. So let's dive in. So RISC-V was architected with this in mind. You want to be able to customize your instruction set for your workloads. And in fact, that's part of the reason I think RISC-V has been so successful in machine learning. There's actually 4 major opcodes. Sorry, I'm a CPU architect by training, so I'm going to geek out just a little bit here. There's 4 major opcodes reserved. That's a lot for custom instructions. Things you can use this for is what you typically think of is I have some specialized arithmetic operation. If you're in ML, that might look like softmax. You might actually also want to do some specialized data movement in and out of your register file, possibly to a secure storage that you don't want to have accessible as part of main memory. Or you could actually tightly couple entire coprocessors and add custom instructions for that. So there's a lot of functionality available to you using RISC-V, but that's easy to say, but there's a real challenge here because unless you have your own CPU design team, how do you do that? If you're licensing IP, it's not your RTL. How do you change that RTL? And most of you, if you're a hardware person, you're not going to do it. That's just crazy, too risky. Even if you do have your own CPU design team, when you do modify it, you have to regression test. You have to make sure you haven't broken anything, right? You have to change the instruction decoder. You have to actually do the RTL for your new instructions. And then, of course, what about all the rest of the collateral, like your instruction set simulator, your C compiler, blah, blah, blah. There's a lot to do, and it's kind of risky. So how do we enable you to customize the CPU for your workloads? So I think the solution is, there's actually 2 parts to the solution. One is you have to have a CPU which was designed and architected from the start to be customized. That's actually the easy part, and I have several slides on the hard part, which is you need to have automation around that. So the CPU, there's a picture here. The purple parts are the parts which are what we call at Andes the automated custom environment extension, excuse me. And we can do that both for scalar instructions as well as vectors, so that's ACE and ACE RVV. But those purple areas are what's covering your decoder for your custom instructions. That's your RTL wrapper around the Verilog, and it does reuse all of the logic for your register reads, your instruction fetches, your write-backs, as well as things like instruction killing. So you want to make sure that that CPU is designed from the start to be added to, okay? That's actually the easy part. The hard part is how do I automate all of that? Because whenever you have a human in the loop, there's always the possibility for problems, and you do have to verify it. So Andy's has a tool which we call Copilot, which enables this. And I'm going to talk about what you as a customer have to input into Copilot, and then what you get out of it. You can see a summary here, but the inputs are, you want to give it your golden model, your System C model. I have a specialized, I don't know, a 10-bit data format, and I want to have adds, subtracts, multiplies, and divides. Based on that, whatever it is, you need to have a System C model which represents what that instruction is functionally supposed to do. You also then need to have a Verilog snippet, and I use the word snippet here on purpose because you don't have to have full RTL. You just need to have the Verilog that implements that 10-bit add or multiply or whatever your specialized function is. It's just that Verilog, and in fact, using Copilot, you don't even have to have all the wires defined. If you have relatively simple design, Copilot will do all of that sort of overhead for you. You don't have to worry about all that overhead of register file access or memory access. All of that's taken care of for you. You also have to give it some meta information like, how many operands does the instruction have, what's the latency, some pipelining behaviors, things like that. So it's relatively simple, and this is all shown by the C semantic, the purple box there that's in red. What do you get out of Copilot? First of all, you get the full RTL. So that's on the bottom right there. We call it extended RTL. That is designed to be literally copied into the database for your processor. That now has integrated your Verilog snippet in with all of the control path. It also will automatically do the opcode decode or opcode assignment and the decode for you if you want it to. It also will insert your functional C model into the golden instruction set simulator. You can do that without having any Verilog. So your software people or your architects can actually try out the new instructions as they go before they even want to talk to a Verilog designer, right? Get the instruction right. We also will enhance or augment GCC so that you can call those new instructions using intrinsics. And since I'm a hardware guy, you also get a test bench. This is all automatically generated for you. It's relatively simple. It's kind of a brute force approach, but for individual instructions, this is a pretty good way to get good verification. It's just going to instantiate your golden model, your Verilog snippet. It's going to compare those cycle by cycle, and it generates random stimulus input for those. Potentially with your input, you as the customer, you can say, I know that I'm gonna have a problem with very small numbers or very large numbers. I want it to focus there, and then you can see a pass-fail. For simple instructions, this might be all of the verification you need. Of course, for more complex full coprocessors, you might want to do more, but the Copilot tool really gives you a head start on your full verification. So this is kind of the flow that we use, that customers use. The left side in green is really for your software people or your architecture team. You don't have to know anything about Verilog to do the left side of it. Although the first thing I tell customers is, if you do the left side without ever talking to a Verilog designer, the architects will come up with something that's impossible to actually design in any reasonable area or speed. So you do have to keep the real world in mind. If I come up with I want to do a 10,000 by 10,000 bit multiply in one cycle, probably it's not going to work. But on the left side, you can completely do test cases, full workloads using your instruction set simulator. Once you've got the instructions that you want, you move over to the right side, you do your hardware design, your verification, you can synthesize, you do PPA. Once it meets the goals, you're done. It's actually that simple. So to summarize, you can add instructions to your CPU. It is possible, the promise is there and the reality is there, but you have to be a little bit careful. And Andes has a solution. I think other IP vendors may also have solutions, but if you want to do this, it's definitely possible. You want to have a sandboxed way of doing it. What Andes has done here is made it so that no matter what you do in that Verilog snippet, it could have thousands of bugs in it. You won't break the baseline RISC-V functionality. So you're always going to be compliant. You can't break the processor. So that's one of the huge advantages you get with this ACE and Copilot system. And of course, we have the automated tool, which gives you all of the collateral that comes with it, your golden models, the full RTL, your decoder, your opcode assignment, and you even get a test bench. So I think this is the right way to do it and the safe way to add instructions to your SoC and to your processor. Thank you very much. If any of you have any other questions, please, I'll be over at the Andes booth, which, like I said, you all passed it on your way in. So it's down there, or me or any one of my colleagues over there can help you. Thank you.